Imagine a bright yellow rock that smells like rotten eggs, erupts from volcanoes and was once called brimstone from the fires of hell. Not exactly the most charming reputation, right? Yet sulfur, this stinky lemon yellow element, is indispensable in our modern world. In fact, without sulfur, your car tires would literally fall apart, crop yields would plummet, and many everyday products and even life itself would not be the same. Welcome to Cube Chemistry, where we will discuss all the elements of the periodic system and also do experiments. So if you like this video and want to see more, make sure to like, subscribe and hit the notification bell so you will never have to miss another episode. Also, make sure to fill in the poll in the post section of the channel for next week, as we will be doing another experiment. To the average observer, sulfur looks like a bright yellow rock or powder. Its color is usually a bold lemon yellow hue, which is its most striking feature. The texture of sulfur can be somewhat powdery or chalky, and pieces of sulfur are often brittle. They can break, crumble easily in your hand. Unlike shiny metal, sulfur does not glitter or shine much. It typically has a dull or waxy surface, a bit like resin, rather than a metallic luster. But probably, of course, what you're wondering right now is, can you lick it? Now, using the periodic table that we will rewrite at some point in the future, it states, go for it. So, yes, you can. It is safe to do and it's not toxic. So, now you can lick it, but as always, we would not recommend you to do so. Now, as you can see, this is one of the more beautiful elements and colorful elements, and I definitely want it in my collection. Now, if you do too, click on the link in the description, use the promo code and get a 10% discount, and you will be helping out our channel. Now, sulfur is as old as the Earth and the universe. It's the 10th most abundant element in the cosmos. It's not some recently discovered element. Humans have known about sulfur since antiquity, because you can literally pick it off the ground in some places. Now, being the 5th most common element on Earth, sulfur often appears in its elemental form around volcanoes and hot springs. Early civilizations couldn't miss it. Bright yellow deposits on a volcano's rim, the choking smell of its fumes, sulfur announced its presence. The ancient Egyptians used sulfur as a medicine. The Ebers Papyrus, a medical text from around 1550 BC, describes an ointment containing sulfur to treat granular eyelids. They might not have known about chemistry, but they observed that sulfur could help certain skin conditions. The ancient Greeks knew sulfur well too. The Greeks burned sulfur as a fumigant against pests and disease, essentially ancient pest control or disinfectant. Physicians and scholars like Pliny the Elder also wrote about sulfur. Pliny, 1st century AD, noted that the best sulfur came from the islands of Aegon, like Melos, and described using sulfur for fumigating, bleaching cloth, and healing wounds. Now, across the world in ancient China, sulfur was known at least by the 6th century BC. Chinese Taoists were fascinated by sulfur's flammable nature and how it reacted with certain metals. They mostly used it in medicine early on, like balms or salves, but eventually Chinese alchemists discovered something world-changing: gunpowder. By the 9th century, the Tang Dynasty era, Chinese writings had recipes for black powder that's a mix of sulfur, charcoal, potassium nitrate, and we basically call it today saltpeter. Now, moving into the scientific revolution, a key figure is Antoine Lavoisier. In 1777, Lavoisier, the father of modern chemistry, conducted experiments burning sulfur and noted that it produced an acid gas, SO2, that could form sulfuric acid with water. More importantly, he recognized that sulfur is an element, not a compound. Now, the industrial age sent sulfur's importance skyrocketing. Why? 2 words: sulfuric acid. Now, sulfuric acid became the backbone of industrial chemistry. It's used to process minerals, make fertilizers, make detergents, you name it. And to produce sulfuric acid, you need sulfur in one form or another. In the early 19th century, a process called the Leblanc process was developed in Britain to make soda ash, used in glass and soap making. And it required sulfuric acid. Demand for sulfuric acid, and hence sulfur, soared. Now, at the time, the main source of sulfur was in Sicily, an island in Italy with numerous volcano sulfur deposits. By the late 1700s and the early 1800s, Sicily was basically the OPEC of sulfur. In 1867, miners in Louisiana found nearly pure sulfur underground, but extracting it was a challenge. The deposits were deep and not in an easy-to-mine ore form. In the late 1890s, Herman Fresh developed the ingenious mining method called the Fresh process. Now, he drilled wells into the sulfur dome, pumped superheated water down to melt the sulfur. Now, sulfur's melting point is low enough for boiling water to do the trick, and then forced the molten sulfur up to the surface with compressed air. Now, this method turned previously unreachable sulfur into an abundant resource. By 1910 or so, the US was producing huge quantities of sulfur cheaply with the Fresh process. So much that America became the world's leading sulfur producer, overtaking Sicily. Fresh technology unlocked massive sulfur deposits and broke the back of the Sicilian sulfur monopoly. Now, by the 20th century, sulfur became even more crucial. The production of sulfuric acid grew exponentially, especially with the invention of the contact process, an improved method to make sulfuric acid, around the turn of the century. Now, sulfuric acid earned the nickname King of Chemicals because nations measured their industrial might by how much of it they produced, and by extension, how much sulfur they consumed. Now, mid-20th century brought a new twist, environmental awareness. Burning all that coal and oil was releasing millions of tons of sulfur compounds into the air, causing acid rain that devastated lakes and forests. Also, many petroleum sources that contain hydrogen sulfide or other sulfur compounds, so-called sour, oil, and gas. Now, to clean up fuels and reduce pollution, governments started requiring desulfurization, removing sulfur from fossil fuels before or during burning. This had an interesting side effect. Sulfur, once a sought-after resource you had to mine, started coming out as a waste product from oil refineries and natural gas processing. By the late 20th century, the main source of elemental sulfur was no longer mines, but a byproduct recovery from oil and gas. When you refine crude oil or process natural gas, you often strip out the hydrogen sulfide. Rather than simply discarding that, industry uses the Claus process to convert hydrogen sulfide gas into elemental sulfur. Now, the Claus process looks something like this, and it creates water and sulfur. The result is tons of sulfur being produced at refineries. Nowadays, if you visit a big oil sands operations or refinery area, for example in northern Alberta in Canada or parts of the Middle East, you might see giant yellow pyramids or mountains of sulfur piled up. Now, that is because we remove so much sulfur to make clean fuels that we often have more sulfur than we know what to do with. In the 21st century, sulfur is sometimes almost an excess commodity, a weird twist from an element once fought over. Sulfur's name carries a lot of history, and we will not be covering it all. The word sulfur comes from the Latin word sulfur or sulfur, which literally means burning stone. In ancient times, people noticed this yellow mineral would burn with a bright flame, so they gave it a name fitting its fiery nature. Now, the Old English name for sulfur was brimstone, famously used in the Bible as fire and brimstone. In fact, brimstone is just an archaic term for sulfur. Now, you've probably also seen the spelling in two different ways. Sulfur with an F and sulfur with a PH. What's up with that? Well, it turns out that that's a little bit of a transatlantic spelling duel. In the US, sulfur with an F has been the standard for a long time, whereas British English used sulfur with a PH for many years. Now, in 1990, the International Union of Pure and Applied Chemistry officially standardized the spelling worldwide as sulfur with an F. Now, let's take a look at a piece of pure sulfur, and the first thing that we will notice is its color. Sulfur is a distinctive bright yellow solid in its native form. In fact, it often occurs as a chunky crystal or powder with a brilliant yellow hue. It's quite eye-catching. Some people think it smells like rotten eggs just by looking at it, but actually pure sulfur is odorless. The smelly reputation comes when sulfur reacts to form certain gases, and we will get to those. Now, contrary to what you might guess, sulfur is not a metal. It's a non-metallic element, meaning it doesn't conduct electricity and it doesn't have that shiny metallic look. It's one of the few elements that are solid and non-metallic at room temperatures. Others include carbon, some forms of phosphorus, etc. Now, one of sulfur's quirks is that it likes to form rings of atoms. Under normal conditions, each sulfur atom hooks up with 7 of its siblings to form an S8 molecule. Imagine 8 atoms connected in a ring, kind of like a crown shape. These S8 rings stack together in crystals, which is how we get a solid sulfur. Now, sulfur has allotropes, which means that it can exist in different structural forms. The most common crystal form is called rhombic sulfur, and there's another form called monoclinic sulfur that can exist at higher temperatures. But okay, unless you are a chemistry student, the specific of crystal systems might not excite you. What's cool to know is that sulfur can also form long chains of atoms when melted. If you heat sulfur gently, it melts into a golden liquid. Heat it more and it becomes a darker reddish-brown syrup. Now, that's actually the S8 rings breaking open and linking into longer chains, making the liquid thick. If you then quickly pour this hot sulfur into cold water, it freezes into a weird rubbery mass called plastic sulfur. Now, the stretchy, bouncy form will slowly turn back into yellow crystals over time. It's a neat party trick in a chemistry lab. You will end up with a substance that's temporarily springy, even though it's made of the same sulfur element. Now, chemically, sulfur is a bit of a chameleon. It sits in the periodic table in group 16 right below oxygen, and like oxygen, sulfur usually forms 2 bonds, like H2S. Analogous to H2O water, except H2S is a nasty poisonous gas that smells like rotten eggs. But sulfur can also form 6 bonds. In some compounds, like sulfuric acid, where it's bound to 4 oxygens or 4 bonds, or go solo with 1 bond, it really has a range of oxidation states, from -2 up to +6, and what that means in plain terms is sulfur is highly versatile in how it reacts. It can grab electrons or give them up, combining with many other elements. This versatility is why sulfur forms an enormous variety of compounds: sulfides, sulfates, thiosulfates, sulfites. An entire chemistry of sulfur exists with many colors, smells, and properties. Let's talk about the smell, shall we, since that is sulfur's claim to infamy. As mentioned, a chunk of sulfur doesn't smell, but when sulfur combines with other elements, the story changes. Hydrogen sulfide, a gas produced when sulfur meets hydrogen, often from decomposing organic matter or certain bacteria, is the classic rotten egg odor. Now, our noses are super sensitive to H2S. Even a few parts per billion in the air can be detected as an unpleasant stink. Ironically, H2S is extremely toxic, far more so than CO2 or many other gases. But our body's alarm system, the stench, usually drives us away long before it reaches deadly levels. Now, beyond the smell, what about fire? Sulfur is quite flammable. It ignites at around 250 degrees Celsius or 482 degrees Fahrenheit. And when it burns, it doesn't produce the typical red or orange flame. Instead, it burns with a strange blue flame that is kind of hard to see in daylight, but eerie in the dark. If you ever get the chance to see a volcano at night, you might witness blue flames at the vents. That's burning sulfur gas. This blue fire is otherworldly, almost ghost-like. Now, physically, sulfur has a low melting point for a solid element. It melts at about 115 degrees Celsius or 239 degrees Fahrenheit, which is quite low compared to metals. It boils at around 444 degrees Celsius or 831 degrees Fahrenheit, turning into a gas of S2 or S8 molecules. Another interesting physical property, sulfur is insoluble in water. You can't dissolve a chunk of sulfur in a glass of water. It will just sit there unchanged. Now, sulfur can often be found in its native elemental form around areas of geothermal activity. If you visit regions of volcanoes, hot springs, or fumaroles, gas vents, you'll frequently see crusts of mounds of yellow sulfur deposits. For example, volcanic islands like Sicily or Io, one of Jupiter's moons, for an extraterrestrial example, are famous for their sulfur. Now we got a couple of minerals here too, and besides volcanoes, sulfur is often locked away in minerals. Common sulfur-containing minerals include metal sulfides like pyrite, which is also called fool's gold, and galena, lead sulfide, as well as sulfates like gypsum, calcium sulfate. So let's get back to the car tires. Well, car tires. What on earth does sulfur have to do with car tires? Well, the answer lies in the process called vulcanization. Vulcanization is a chemical treatment of rubber that gives it strength, elasticity, and durability. Without vulcanization, natural rubber is a bit of a mess. It's tricky. It can become brittle in cold water and gooey in hot water. Not ideal for a tire that has to handle summer heat, winter chill, while carrying a car's weight. Now, sulfur is the key ingredient in vulcanizing rubber. When you mix raw rubber, which is made of polymer chains of isoprene, with sulfur and heat it, something magical happens. The sulfur forms bridges between those long rubber molecules. These bridges are sulfur-sulfur bonds, creating crosslinks that tie all the rubber molecules into one interconnected network. Now think of it like this. Raw rubber is like a pile of loose spaghetti strands. They can move past each other too easily. Vulcanized rubber is like a net or a web. The strands, polymer chains, are linked by sulfur at various points, so they can't slide freely, and the material becomes tougher and more elastic. The result of vulcanization is rubber that doesn't melt or turn gooey in heat, doesn't crack as easily in cold, and has improved resilience. This was a world-changing discovery. In 1839, American inventor Charles Goodyear famously found out, legend says by accident, dropping a sulfur and rubber mixture onto a hot stove, that heating rubber with sulfur could cure it. He spent years perfecting the method and got a patent in 1843. He named the process vulcanization after Vulcan, the Roman god of fire, a nod to the heat and brimstone sulfur needed. Since then, vulcanization has been the cornerstone of the rubber industry. Car tires, bicycle tires, shoe soles, rubber bands, hoses, basically anything made of natural rubber or many types of synthetic rubber has likely been vulcanized with sulfur or sulfur compounds. Now, if you drive a car, each of your tires might contain about 1 to 2% sulfur by weight, bonded into the rubber. It's not a lot, but without that small percentage, the tire wouldn't hold up to the task. So yes, every time you take a road trip, quietly doing its job, in your tire is a bit of that disgusting yellow rock, making sure your rubber is firm yet flexible. Now, fun fact, those sulfur crosslinks in tires are actually analogous to something in biology, the disulfide bonds in your hair and skin proteins. If you've heard of hair perms or the smell of burning hair, that's sulfur bonds breaking or reforming. Sulfur links things in both living tissue and in our manufactured materials to provide structure. The single biggest use of sulfur by far is in production of sulfuric acid. In fact, roughly 80 to 90% of sulfur consumed goes into making sulfuric acid. Why such a big appetite for one acid? Well, sulfuric acid is unbelievably important for industry. It's used in manufacture of fertilizers, chemicals, petroleum refining, mineral processing, explosives, batteries, cleaning agent, the list is long. One of the primary uses of sulfuric acid is to make fertilizer. The world needs to feed billions of people, and fertilizers are essential for high crop yields. The most common fertilizers contain nutrients like nitrogen, phosphorus, and potassium. NPK on fertilizer bags. Phosphorus in fertilizers usually comes from phosphate rock, which is basically mined calcium phosphate. But that rock isn't readily usable by plants, so we treat it with sulfuric acid to produce superphosphate, a plant-accessible form of phosphorus. This reaction consumes tremendous amounts of sulfuric acids globally. Sulfuric acid is also used to manufacture phosphate-based detergents. To refine petroleum, for example, some refining processes use sulfuric acid to remove impurities, to pickle clean metals in fabrication, and to produce countless other chemicals, dyes, pigments, drugs, etc. If you look at a chemical plant complex, chances are sulfuric acid is involved somewhere. That's why economists sometimes consider sulfuric acid output as an index of a country's industrial activity. So, how do we make sulfuric acids from sulfur? Well, usually by burning sulfur to get sulfur dioxide, then converting that to sulfur trioxide using a catalyst. That's the contact process. And then reacting sulfur trioxide with water to get sulfuric acid. It's an exothermic process and can be done on vast scale. So essentially, a lot of sulfur we produce is intentionally burned under controlled conditions to make acid. It's kind of funny. We spend effort pulling sulfur out of oil, reducing air pollution, then we turn around and burn sulfur in a factory to make acid. But at least that burning is captured and turned into a useful product, not vented freely into the air. We touched on fertilizer in relation to sulfuric acid, but there is more. Sulfur itself is an essential nutrient for plants. It's not needed in huge amounts like nitrogen or potassium, but it is critical for protein formation in plants, since the amino acid cysteine and methionine contain sulfur. One common form is gypsum, calcium sulfate, which is both a soil conditioner and a source of sulfur and calcium. Also, elemental sulfur can be spread on fields. Microbes in soil will slowly oxidize it to sulfate that plants can use. If you see fertilizer bags and one of the ingredients is sulfur or sulfate, now you know why. Gardeners and farmers have long used elemental sulfur powder as a fungicide. If you grow grapes or roses, you might be familiar with dusting sulfur. It's an approved organic treatment for powdery mildew and other fungal diseases. The sulfur essentially sublimates, turns to gas slowly on the plants, and the vapor or direct contact controls fungi and some pests. It's one of the oldest known pesticides. Elemental sulfur has been used in dermatology for ages. It has mild antibacterial and keratolytic skin peeling properties. Sulfur ointments or soap have been used to treat acne, seborrheic, and dermatitis and other skin conditions. If you ever smelled some old school acne creams or maybe lice treatment in shampoos, that faint match smell is sulfur or sulfur compounds. It's not the first line treatment these days, but it's still around as an option. MSM stands for methylsulfonymethane, and it's a natural form of sulfur that people often take as supplement. MSM looks like a white powder with no smell, and it gives the body sulfur it needs to build things like healthy skin, hair, nails, and joints. Some studies have shown that MSM may help with joint pain, stiffness, and inflammation, especially in people with arthritis. Most people can take it safely, and it usually doesn't cause any side effect when used in normal amounts. We'd be remiss not to circle back to sulfur's booming role in history. Gunpowder or black powder is the classic explosive propellant, consisting of 75% saltpeter, potassium nitrate, 15% charcoal, and 10% sulfur. Proportions can vary. Now, sulfur's role in gunpowder is to lower the ignition temperature and to help the fuel, charcoal, ignite the nitrate oxidizer quickly. When gunpowder burns, the sulfur also helps to produce a smooth, fast burn rate and contributes to the formation of gaseous products. Without sulfur, charcoal nitrate mix can still burn, but much less reliable. So, from medieval cannons up until the late 19th century, when modern nitroglycerin-based explosives and smokeless powder replaced black powder, sulfur was an essential ingredient in warfare and mining explosives. Even today, black powder is used in some fireworks and safety fuses. That distinct rotten egg whiff after fireworks go off, that's traces of sulfur compounds from the black powder. Next time you watch fireworks show, remember there's a little bit of elemental sulfur helping light up the sky. Sulfur sneaks into a lot of processes. For instance, the paper industry historically used sulfur compounds like sulfites in pulping process to break down wood chips into pulp. The sulfite process of making paper was common for a long time, though less now, replaced by other methods. Those sulfide mills often had a distinct sulfurous smell. In old school photography, if you ever developed a film or prints the traditional way, you encountered a sulfur compound, sodium thiosulfate, commonly called hypo. This was used as a photographic fixer to dissolve unreacted silver, halide, from film or photo paper. It's basically a sulfur-containing salt that can stabilize photographs. Photographers might recall the rotten egg smell that could arise if fixer went bad. Yes, that's sulfur again. Thiosulfate. Now, sulfur also finds uses in making matches. The tip of the safety match often has a bit of sulfur in the ignition mix, along with other chemicals like phosphorus compounds and oxidizers. The sulfur helps the match head flare up and also contributes to that unique smell of just struck match, sulfur dioxide whiff. With the rise of electric vehicles and renewable energy, researchers are developing lithium-sulfur batteries. Sulfur is cheap and can store a lot of energy per weight when paired with lithium, potentially leading to batteries with higher capacity. These aren't mainstream yet, but perhaps in the future. Sulfur will be in your car, not just in the tires, but also in the battery that propels it. And remember those giant sulfur piles? Well, some clever uses have been found for those, forming solid sulfur into blocks for long-term storage, as mentioned, and even grinding it to make sulfur asphalt or concrete for construction. Sulfur-based concrete doesn't need water. It's set by cooling, not by hydration, like Portland cement, which can be useful in very cold regions. But there is more. Ever cut an onion and started crying? Thanks sulfur. Onions and garlics are rich in organosulfur compounds. Cutting an onion triggers enzymes that generate, well, you pronounce this one, a volatile sulfur compound that wafts into your eyes and makes them burn with tears. Garlic pungent aroma comes from sulfur compounds like allicin. These molecules are actually beneficial in small amounts. They have antibacterial properties and contribute to flavors we love in cooking. So the delightful smell of a sautéed garlic, that's sulfur working its magic in the kitchen. Utility companies add a compound called tert-butyl mercaptan and related thiols to otherwise odorless natural gas so that leaks can be detected by strong rotten cabbage smell. Mercaptans are sulfur compounds. Our noses are ultra sensitive to them, even more so than hydrogen sulfide. This is a case where sulfur's stink is life-saving. It warns of the dangers, gas leaks, before an explosion can occur. If you ever visited hot springs or thermal baths, you might notice the sulfur smell. Many hot springs, like those in Yellowstone or Rotorua in New Zealand, contain dissolved hydrogen sulfide from underground. Sulfur-rich mud and waters have been used as health treatments, sulfur baths for conditions like arthritis, skin issues, a practice going back centuries. Now, believe it or not, you're carrying sulfur inside you right now, about 140 grams of it if you weigh 70 kilos, around 150 lbs. Sulfur is present in every cell, mostly as part of amino acids, which make up protein. The keratin in your hair and nails, for example, is rich in sulfur bonds, hence burning hair smells sulfury. Sulfur is also in the B vitamins biotin and thiamine. Now, sulfur dioxide from burning coal without scrubbers can cause respiratory problems and contribute to smog. Historically, London's infamous pea soup fogs and the Great Smog of 1952, which killed thousands, were largely due to sulfur dioxide and soot from coal fires, reacting to form a shocking acidic haze. This prompted big changes, like the Clean Air Act in the UK and similar moves elsewhere to reduce sulfur emissions. Now, as mentioned, SO2 and nitrogen oxides in the atmosphere create acid rain, which in the late 20th century was killing fish in lakes and dissolving marble statues. It was largely addressed by reducing sulfur emissions from power plants via flue gas desulfurization units, basically scrubbers, that often produce gypsum as a byproduct. So next time you hold your nose at a geothermal spring or smell a freshly lit match, remember, there's a bright side to sulfur. Without it, our world would literally not run. Our engines, our crops, our lives depend on a healthy dose of brimstone. Sulfur may smell like the devil's doing, but it's truly a little bit heaven for modern conveniences and necessities. Now, if you think we missed anything, let us know in the comments, and if you like this video and want to see more, make sure to like, subscribe, hit the notification bell, so you will never have to miss another episode. And also, if you want to know more about phosphorus, watch this video next.